Hi again, and welcome to part 2 of lesson 2 of the Classiq bootcamp. In the first lesson, we've seen how to use and explore quantum algorithms and applications using the Classiq IDE. We discussed the process from selecting the application or the algorithm, synthesizing a circuit, executing it, and analyzing the results. In the previous video, the first session of this lesson, Yuda taught us about high-level functional design and its importance. Now, we will dive deeper with concrete examples and explore its advantages. We will see how functional design allows us to optimize an algorithm for minimal circuit depth and then to re-optimize the same algorithm to achieve minimal circuit width. We will consider various constraints like the maximum number of qubits. Our first example is learning functional level design with the Grover algorithm. After synthesizing it, we obtain a quantum circuit. This circuit prepares two quantum registers in specific states. Quantum register A can take values from 0 to 3, and quantum register B can also take values from 0 to 3. Using the Grover operator, we aim to find solutions where A plus B equals 4. This results in three possible solutions: A equals 2 and B equals 2, A equals 1 and B equals 3, and vice versa. Executing the circuit using the air simulator confirms these results. We indeed receive three possible results. 1 0 1 0 means 2 plus 2, 0 1 1 1 means 1 plus 3, and 1 1 0 1 means 3 plus 1, so indeed the algorithm is working as expected. In fact, in this example, we incorporate previous knowledge that A and B cannot be 0. If A equals 0, B needs to be 4, but it is limited between 0 and 3 because we allocated only 2 qubits for each register. Therefore, we prepare the states of A and B to be an equal superposition of 1, 2, and 3, without the 0. As we can see by this red line, the circuit involves an auxiliary qubit, and its purpose will become clear shortly. We can see the circuit details here on the left. First, we see the circuit depth, which is 495, and the number of qubits is 6. Let's zoom in inside the Grover operator. We see an arithmetic oracle and a Grover diffuser. Now we can understand that the auxiliary qubit that we have seen is used by the arithmetic oracle. But the auxiliary qubit is not merely an auxiliary. It is used for the phase kickback, a common structure in quantum algorithms. Now, when we zoom in into the arithmetic oracle, we encounter for the first time the multi-control knot. The multi-control knot, also called the MCX, is of high importance in quantum algorithms, and especially in the optimization the Classiq engine applies. In this example, we have 3 control qubits and 1 target qubit. When the state of all control qubits is 1, the state of the target qubit should flip from 0 to 1 and vice versa. Now let's focus only on the MCX implementation. We can open it up and view the implementation of this circuit as it decomposes into 1 and 2 qubit gates. This MCX can be generated from the synthesis page. We just need to change in the model what is the number of control states we want, 3 in our example. Okay, so we have the Grover algorithm with the MCX within it. What's next? We want to generate the same algorithm with shorter depths at the expense of more qubits. A motivation for shorter depth is that it is one of the main factors leading to errors on today's quantum computers. Here we can see the exact same algorithm, our Grover algorithm, but now it is optimized for shorter depth. We can see that the parameters of this circuit are different. The circuit depth is 411 compared to 495 we had previously, on the expense of the use of 7 qubits compared to 6. This is the first example and the first time we encountered 2 different circuits implementations of the exact same algorithm. Let's understand what is actually different within the implementation. When we zoom in into the Grover operator again, we still see the arithmetic oracle with the phase kickback. Now when we zoom in within the arithmetic oracle, we see an MCX with 1 auxiliary qubit. The functionality of this MCX is the same, applying a NOT gate on the target qubit when all 3 control qubits are in the state 1. But here, for the implementation of this MCX, there is one additional qubit that enables the circuit to be shallower. Let's focus only on the MCX with 1 auxiliary qubit. We can see that the depth of this MCX is only 22, with 5 qubits, compared to the depth of 27 for the MCX with no auxiliary we had before. The implementation of this MCX is completely different from the implementation of the MCX without the auxiliary qubit. Now, when you go back to the Grover algorithm, we can see the implementation of the MCX with the auxiliary within the Grover algorithm, and the implementation of the MCX without the auxiliary within the Grover with fewer qubits. So what we have seen here? This was the first example we covered that we actually saw under the hood that the same algorithm can have several implementations. We started with the same functional model, the same algorithm, and synthesized it once for short depth and once for short width, and we actually received these two implementations according to what we wanted. Now we've started to scratch the surface of why functional design is useful. Okay, but I can understand people that might say this is only a small example and not really useful. Sure, this was our first educational example. Let's go now into a larger example that results in a large difference between its implementations. We will continue with our MCX, but now we will choose one with 14 control qubits and one target qubit. We optimize it once for depth and receive an implementation with 21 qubits, 5 of which are auxiliaries, and depth of 36. But when we optimize for width, we receive an implementation with only 16 qubits, at the expense of a very large circuit depth of 885. So here we can start already to see large differences between different implementations of the same functional building block. We have a circuit depth of 36 on the one hand, compared to a circuit depth which is 25 times larger, with 885. This is already a difference that can make a real impact on the success of some implementation of a quantum algorithm. But it's not that we can only optimize for depth or for width, we can do more. We can impose some additional constraints and to receive an intermediate implementation. For example, here, we want to optimize this 14 MCX for the shortest depth, but to use only 18 qubits. We receive the circuit that uses all 18 qubits with a circuit depth of 315, which is less than 885, but is more than 36. Okay. Where can we see this 14 MCX in real quantum algorithms? Let's see together. We choose now a larger example of the Grover algorithms, where we have a nice API on the right to change the expression we are looking for. We want to choose for the solution of the equation a plus b plus c equals 84, where the values of a and b and c are stored in 5 qubits registers. This kind of algorithm can have some underlying applications, like white box fuzzing in cybersecurity. The synthesis of our Grover algorithms gives us this circuit. And now, when we zoom in, we can actually see our 14 MCX. So it's not just a standalone building block, it is actually used in several of the most common quantum algorithms. I hope you enjoyed this part of lesson 2, and you have a better feeling now of what does it mean high-level functional design and how it can actually be utilized to generate substantially different circuits implementations for the same quantum algorithms.